So, anyway, moving on. I want to try something a little different today. I'm going to talk some science stuff because I've had some requests from when I first started this channel that I do some science stuff, and I've kind of gotten consumed with doing mostly political and just general thought commentary. But I do want to occasionally do some science stuff, so I'm going to do some quick little short little conversations with myself on 3 of the coolest things that I have ever learned from my exploration into the scientific world. Now, I am not a college-educated physicist or any kind of scientist at all. The thing that I know the best professionally is steel processing, and that is not a particularly high-level field. You can pretty much learn it without going to school as long as you know some basic math. It's not an unskilled job, just not particularly difficult as far as academics goes. So everything that I know is just picking up concepts. I haven't done any of the math. I haven't done any of the experiments. Obviously, it'd be really hard to do a lot of physics experiments in your house, but high-level physics experiments in your house. But I have spent a lot of time trying to nail down the concepts, so I'm going to try to explain a couple of concepts here. And the first one is going to be quantum tunneling, which I thought was just ridiculously cool the first time I learned about it. So, all right, let's bring this up. Okay, so go to our lovely friend Microsoft Paint here because we are fancy. All right, so you have what is this line here is, we'll call it space, right? So this line is space, and and then this line is space. So we well, that didn't work. I guess I'll just draw a line. Sorry, I should have prepared this beforehand. Okay. Let's go back to... Does my marker work? Hey! Marker does work. Hey, my cat just came in. What's up, Fifi? What do you want? I shut that door for a reason. What are you doing? You never come in this room unless I'm in this room. What are you doing? She's sniffing stuff. So, oh, she's hunting for pets. She wants some love. Well, if you want some love, you got to come over here. Fiona, come here. Come here. Come say hi. Come here. Come on. Come on. Come on. She's being a fraidy cat. Come here, Fifi. Screw it. She won't come say hi. So anyway, in quantum mechanics, shut the door. Okay, you gonna leave? Stay out. In quantum mechanics, a particle does not have a defined position. So, like, if you throw a baseball through the air, at any given point in time, you know where the baseball is. You can see it. It has a spot, right? But in quantum mechanics, this is not the case. Things don't have a position. Not that we don't know the position, but it literally doesn't have a position. This is something that we have proven as with as much certainty as is reasonably possible to expect. It's at this point a fact. There may be slightly different interpretations of what it means, but for all intents and purposes, particles don't have a position. They have a distribution, a probability of being somewhere at any given point in time. And that probability of being somewhere at any given point in time has a curve to it that makes it to most likely be in a given area. This is why the position of objects in the world don't just, they don't just randomly fly apart with any regularity, is because the probability of finding a particle in a given space is higher in the local area where you would expect to find one. So if there's an electron around an atom, it doesn't have a defined position, but you're most likely to find it in the area around the atom. So the way that we draw that on a graph would be this curve right here, which is very poorly drawn. So I think I'm going to try to redo this line. Maybe. Okay, so that looks more, that's a little better. Okay, so imagine this is your position. This line at the bottom is your position. Then normally a normal object would have a very defined position. So this bit right here, that bit right there, pardon my drawing skills, this tells you that your baseball, right, is 100% to be found in this spot, this spike right here. So it's not going to be found a couple inches to the left. It's not going to be found a couple inches to the right. It's going to be found right there, right where that spike is, right? That's how things normally work. You see a baseball, there's the baseball. But in particle physics, things don't have a defined location. You may find it over here. This spot right here. You may find it here. You may find it here. You may find it in this spot. You may find it in this spot. And the height of the curve here is the probability that you will find it there. And but it is possible, although less likely, that it will end up over here 5 inches to the right. So you'd be looking at your baseball and then just boom, it just shows up right there. And you won't know where it shows up, where it will be, until it interacts with something. So the baseball does not have a position at all. It's just this sort of like cloud of it might be somewhere, right? And then as soon as the baseball interacts with something, it seems to just choose a position. And the probability of finding it in one of the positions that it chooses increases the closer you get to the top of this curve, right? So if you build a wall, this is the limit that they're coming up to with computers, right? If you build a wall that is smaller than this curve, right? Right here. So imagine you're building a computer and you have transistors in it. There's electricity flowing around, right? Little electrons getting trapped in gates that make up your ones and zeros in your computer, right? You want those electrons to stay in the area that they're supposed to stay. If they don't stay there, that's your data getting corrupted, right? You need those ones and zeros in the right place in the chip in order for the chip to function properly. And the problem is we are starting to get to the point where we can make transistors that are smaller than the space that a free electron might be in. So the probability of finding the electron on the other side of the wall, which is what these two lines represent, is not 0. It's a non-zero chance. Most of the time, the electron is here, in between the two gates of the gates of the transistor in the computer. But occasionally, and this is something that just blows my mind, if your gates are small enough to where the probability distribution of where the electron may end up once it has an interaction, if enough of the probability distribution is outside the gate, then randomly the electron will just show up. It'll just decide totally randomly to be outside of the transistor gate, and then it just flies off into the rest of the system and corrupts a bunch of data. So there's like a minimum size that you can make a transistor and trap an electron inside of it to make a computer function, because the smaller you get, once you reach a certain limit, the electrons in the system just decide to not be held in by the walls of the transistor. They just, for all intents and purposes, teleport to the other side of the transistor and just off into the distance. And that blew my mind, because normally what we think about is if you build a wall, no matter how small the wall is, like here, right? You have a 100% chance of the baseball being between the wall. If you take the walls and you close them in upon a baseball, it doesn't matter how close you bring those walls. The baseball will never end up on the outside of the wall. You'll just crush it. It'll just come down, right? But in particle physics, the math says that this should happen, and then in practice it does happen, where as the walls get closer and closer and closer and closer, eventually you reach a size where the particles inside the walls just teleport out of it. They just show up on the other side, fuck off into the distance. And this is this very interesting problem that physics has not fully understood the implications of yet. That we know that it happens. We have math to describe how it works, but we're not entirely sure what it is. This is an area where the interpretation of the math is up for debate. We know that it works, or that quantum tunneling happens. We know that things seem to teleport through walls, but we're not entirely sure what the implications of that are. We have math to describe or what will happen when quantum tunneling behaves. It's kind of like, it's kind of like having math to describe what gunpowder does, but not understanding exactly what gunpowder is. Like you know what happens. You have all of the math to describe what the gunpowder will do, but what the gunpowder is a different question. And that's basically where we are with physics at this point, is we have math to describe what particles do, but we don't actually know what the particles are. And the implications of quantum tunneling are varied and hotly debated in physics. But I thought that was just really cool, that like walls are not walls in particle physics. Like once you reach a certain size, the rules that the normal world behaves in just don't matter. It's just a completely different world down there. And I just thought that was really interesting. So